We're going to be learning about symmetries in natural laws. And the end goals of this lesson are to define symmetry in the mathematical sense as opposed to colloquial sense, and to identify some interesting symmetries underlying natural phenomena. Okay. And just before we get into that, I would like you to click on the first link in the chat and go to the column under your name and just type in some simple yes or no to indicate whether you think that the object listed possesses some concept of symmetry as you would define it. Okay, can you do that for me? It shouldn't take more than a minute.
Yeah.
Great. So the answers are kind of how I expected them to be. Let's review these. So when we think of symmetry, probably the first thing that comes to mind is symmetry under a reflection in a mirror, right? So the letters M and A have a mirror symmetry in the vertical direction. The letter D has a mirror symmetry in the horizontal direction. Whereas the letters G and S don't seem to have an obvious mirror symmetry. That's why some of you mark no for that. The letter O has symmetries, mirror symmetries in any direction, right? Yet another symmetry that we could think of is what is known as flip symmetry. This is not quite a mirror image, but if you rotate these letters by 180 degrees, you end up with the same letter, right? So even though S, the letter S does not have a mirror symmetry, it still possesses some kind of symmetry. Now that gives us a definition, a mathematical definition of what we mean by a symmetry, which is if you do something to an object and nothing changes in that object, then you say that that object is symmetric under that particular operation. Okay. So to illustrate with the examples we just saw, the letters M, A, and D are symmetric under the operation of reflection. The letter S is symmetric under a flip or rotation by 180 degrees. This weird object called a triskelion is also symmetric, but not under a mirror image or anything. It's symmetric under a rotation by 120 degrees. Now, can you guess what the letter O is symmetric under?
All of them?
Yeah, all of them. In particular, it's actually even more symmetric than that. It's symmetric under rotation by any angle, right? It is a circularly symmetric object. Now, all these are examples of symmetry in the domain of space, but you could also imagine symmetry in the domain of time, right? There's nothing that stops you from that. So, for instance, there is symmetry under time reversal. And a good example of that is imagine watching a video of a lamp doing nothing but just sitting there and shining light. Now, it doesn't matter whether you play this video in the forward direction or the reverse direction, right? The video is going to look the same. That's symmetry under time reversal. Okay. Now, it's important to distinguish between physical phenomena, such as those we saw, and the natural laws or the physical laws underlying these phenomena. And the useful analogy for that is think of the physical world around you and phenomena in it, such as an apple falling from a tree or planets going around the sun. Think of these as the operating system, and think of the underlying mathematical laws, such as Newton's law of gravitation in this case, as the computer code for this operating system. Okay. Well, now nature might have symmetries built into this code. For instance, in this equation, replacing r with a minus r or displacing the masses by the same amount doesn't change the law. But that doesn't mean the natural phenomenon that we are looking at, that an apple falling under a tree would look the same under a mirror, right? So it's important to distinguish between symmetry inherent in the mathematical law versus the symmetry manifesting itself in the natural phenomenon that it describes. Now, that brings me to what particle physicists like me do today for our living. Okay, it just comes down to this. This is a very accurate statement. What we do is to guess the symmetries in nature's code, and using that guess, try to uncover what this code is. And when we do that, often we find that this code is inconsistent with the observations of physical phenomena around us. And so the way we try to solve that is to guess even deeper symmetries in the core of nature. Okay, and so we're just trying to uncover as many symmetries as possible in nature, and that way try to understand why the physical world looks the way it is. And this program was inaugurated in 1905 by Albert Einstein. Everybody knows that Einstein did something astonishing, but this is an exact statement of what it is that he bequeathed us. Okay, he told us that nature respects what is known as a Lorentz symmetry, which is a symmetry under shifting an observer to a frame of reference, which I believe a concept I believe that Mac is going to be talking about. A frame of reference that is moving with a constant relative velocity with respect to the observer. Okay, and this is what is known as the principle of special relativity. Now, before I end my lecture with a little activity, I just want to mention that another very powerful guideline that physicists like me use in this hunt for symmetries is a powerful theorem proposed by my favorite physicist, Emmy Noether, whose life and work I highly encourage you to go and read about. I'm not going to be talking about the theorem, but I would like you to go home and read about it and reflect upon it. It's one of the most beautiful theorems in physics.